Now next, I'd like to introduce a class of very special members. They're called zero force members. What they call zero force because, as the name suggests, there's zero force in it. There's no load in the members. Okay? And the next question is, why are they there if there's no force? There's no load in it. It's not sharing any load. It's not doing anything. It serves no purpose. Well, let's push the discussion to later. Okay? Let's first look at a sample truss. And let's first do some calculations and find out if any of the members is a zero force member. Okay. Let's say I have a truss like this. Okay? And each member across the bottom chord has equal length. Okay? And across the top chord, same thing. Okay? So equal length. And all the slanted members have 45-degree angle. And that's it. Let's do some calculations. Now, I have a load applied at this joint E. Okay, straight down, 200 newtons. Okay. So that's a given problem. And that's very typical. Okay, how a truss calculation problem can be given. Right? So, you're asked to find all the forces in each of the members. Okay, first thing you want to do is label everything. Label all the joints. Okay, now notice I've labeled just one half of this truss. Now you've done some calculation, some problems so far. You notice that if a truss is symmetrical, then whatever force that you calculated here in this member is exactly the same as this member. Okay, they're exact mirror image. Okay, so however much this force is, whether it's compression or tension, will be exactly the same here. Right? So this guy, exactly the same as this guy in terms of loading. Okay? So I only need to calculate one half the truss. Next thing is, knowing that this is 200 newtons coming down, that's the external load, then immediately I know that there are two reaction forces coming back up, assuming that they're symmetrical. Okay? So 100 each. Right? So half of that. Right? So this whole truss as a free body diagram, okay, is balanced. Right? So it's in equilibrium. Next, pick a joint. Right? Using the joints method like we've been talking about. So first joint you pick is joint A, because this joint A has no more than two unknowns. Right? This FAC and FAB. Right. So let's do that. Okay? So if you've done enough calculations so far, this should come quite naturally. Alright, you should be able to do this very quickly. So I have this 100 newtons coming up, and then I have these two forces, FAB, FAC, and then to figure out the direction of these two guys, well, I should first can figure out this guy, right? Because this 100 newton goes up, so the y component of this FAB, I call it FABY, must point down to counter this guy. Alright, so since the y component points down, the x component points to the left. No other choice. And since the components goes this way, then FAB itself must go into the joint. Okay? And then this FAC direction must counter this FABX. Alright, horizontally. So it goes to the right. Okay. Let's do some calculations. Alright, so some forces, x direction equals 0. Some forces y equals 0. Since I know the y force, okay, that's given, so I'm going to start with this. So 100 minus FABY, that's it, right? So no other vertical force. So FABY equals 100 newtons. Okay, so I know this is 100. And since it's a 45-degree angle, so this triangle right here is an isosceles. 45, 45, 90. Right? So this means that these two sides are the same. So, therefore, from geometry, FABX also equals to 100. Right? And knowing this triangle, you can easily find the hypotenuse, FAB itself. Okay, so we can use sine 45 degrees or cosine 45 degrees, right? Or use hypotenuse, the Pythagorean theorem. So FABX squared plus FABY squared, right? So not 0, right? So that's 100, right? So it's 100, 100, so square plus 100 square. Just crunch number. And turns out to be 141.4, right? Or square root of 2 times 100, right? So to be exact, right? So if I can round up, that's fine, right? Alright, so FAB is this much, okay? And we can come back to this equation then, right? So since we started with this equation, come here, so let's continue on, right? So this, so FAC minus FABX equals 0, therefore FAC equals FABX, which is 100. Okay. So, there you have it. That's your answer for the first joint, right? And I'm going to write down the answer here. So FAB is 141.4 Newton. And since it goes into the joint, it goes out that way. Again, using Newton's third law, this is compression. FAC is 100 Newton. And since this goes away from the joint, and this is tension. Okay, AC is under tension. Okay. First joint is done. We've used joint A, we figured out these two, and obviously AB and AC is not a zero force member because they each have a force in it. Okay. Keep going. Now, the next joint I'm going to go to is a joint that has no more than 2 unknowns. Okay, always pick a joint that has no more than 2 unknowns. So, let's say if I do joint B, see B has 4 members attached to it, and only one of which is known, which means that B would have 3 unknowns, so that's no good. So the next joint to go to is joint C. Joint C has 3 members attached to it. One of them is known. We just calculated it. This means that it's left with 2 unknowns. So joint C is good. So let's draw that. Okay, so I have this 100 here, and then I have this other guy, CE, and then this CB. Right? So just label it CE, F, B, C. Since this 100 is tension, okay, and so this 100 Newton, okay, should be going away from the joint, right, going back into the member AC, right, and this is FAC right here. Okay, so next step, figure out the direction of these 2 arrows. Now, FCE, okay, has to counter this FAC, okay, horizontally, so it has to go to the right. Okay, what about FBC? FBC, we don't know the direction at this point. So, let's just assume a direction. If you don't know something, assume it. Okay, that's okay. In engineering analysis, oftentimes, you don't know something, assume something, and then do the calculations according to your assumption. Okay? I'm going to assume that it goes up. Right? So, assumed up. Okay, let's do the calculation. Some forces, x equals 0. Therefore, FCE minus this 100 equals 0. Therefore, FCE equals 100 newtons. Simple as that. Okay, so the 100 newton goes away from the joint, so FCE is 100 tension also. Okay, here's the next equation. Sum of forces Y equals 0. Looking at this whole free body diagram, expand the left hand side. So sum of forces Y, I have F, B, C in the Y direction. I reckon nothing else. Nothing else is in the Y direction. So that's it. That's it on the left hand side. FBC is 0. FBC is 0. There's no force in BC. BC is a 0 force member. There you have it. That's how you prove that a member is a 0 force member, by going through the calculation, by applying these two equilibrium equations, right? So scientifically, you calculate that BC is a 0 force member. There's no force in it. Okay. So a member like BC is called a 0 force member. Right? And why is it here? Can we take it out? Can we just eliminate this BC from this whole structure, from this truss? Well, sure. Theoretically, it's okay. We can take it out, no problem, since it shares no load. Okay. However, practically, sometimes some 0 force members do need to remain in the structure. Okay, and that's because during actual loading, okay, a truss, which is one part of a bridge, an entire three-dimensional bridge. So a bridge has two trusses, right? And under actual loading, sometimes a bridge will be under uneven distribution of loading. Okay? So one truss might be under more load than the other, and one side of the truss could be under more load than the other. And also, bridge could experience twisting, some kind of warping, right, due to external effect, like wind, right, or uneven distribution of loading, right, cars and people and things like that. So, in that case, BC in reality might actually have a load in it. Okay. So, some 0 force members should remain in the truss, although in theory, in this calculation, it's 0 force in it. It shares no load. Okay? But practically, it might. Right? Okay. So, BC is 0 force member. Right? And then you can proceed into the next joint. Joint B will be the next joint. Right? And move on to the other joint. And then, once you figure out all the forces in one half the truss, then you can just mirror image it. Okay? So this would be 141.4 compression and so on. And if you actually go through the calculations, you will also find that this DE is also a 0 force member. Obviously, this is 0 force also. And one kind of trick that you can tell whether a member is a 0 force member is that if it's a part of some kind of T structure, whether it's a upright T or reverse T, then this guy is a 0 force.